start recording. Oh, I think everything is fine now. Today our plan is the following. We continue with optimization with inequality constraints. We continue with optimization with inequality constraints. And today we will cover two topics: inequality constraints. Basically, we're working on these topics for the third week. And today we will cover special types of constraint, because in many economics problems we encounter non-negativity constraints. So basically, very often we work with constraints like x is greater or equal than 0, y is greater than equal to 0, and we can be a little more parsimonious. We can save a little bit of time and not introduce additional Lagrange multipliers. So there is a parsimonious way to introduce equalities like that. This will be the first topic. And then what else? And we will cover second order sufficient conditions a little bit in more details. That will be two topics for today. As always, if you have any questions, just don't be shy, be brave, and ask them. It's you have a good opportunity at the beginning of every lecture, and ask your question if something was unclear in the past, or even general math questions. I like solving problems. If you have something that is not clear, then just go ahead.
It's okay for me.
Okay, so let's continue. Let's consider non-negativity constraints. So let's provide some example, like let me find some problem from the past exams. Yeah, I think like this. We have a problem, maximize x plus logarithm of y, given a lot of constraints. Given x is greater than 0, x plus y is less than 4, x plus 2y is less than 6. So let's consider the problem like that. What we can do? We can, so when you have a special type of constraint, non-negativity constraint, you can work with these constraints as usual. So you can introduce lambda, or you can use another method. So let's first the standard approach. Standard approach is to introduce all Lagrangian multipliers. So the standard approach will be, let's restate the problem, maximize x plus logarithm of y. I restate all the constraints like x is greater than 0, 4 minus x minus y is greater than 0, 6 minus x minus 2y is greater than 0. And I can certainly write Lagrangian function. Sorry, I need to check in DCQ first. Let me check in DCQ first. And I see, oh, I need to consider what constraint can be active. Yeah, maybe this one is active, maybe that one is active, maybe the third one is active, but I see that my constraints are linear. Maybe two are active, or maybe even three are active constraints. So let's consider quickly all these cases. I have a lot of cases to consider, but we are brave and we are full of energy. So let's consider these cases: A, B, C, D, E, F, G. Okay, so case A. Case A, I have only one first constraint. Jacobian matrix is 1, 0. I'm happy, it has full rank. Rank is equal to 1. Case B, Jacobian matrix is who can help me? I'd like to be
-1.
Yeah, I'd like to be accompanied by brave warriors to kill this problem. Okay, and the rank is 1. Oh, I'm happy. C, the Jacobian matrix is -1, -2, because I consider derivatives only of active constraints. And I'm once again happy, because rank is 1, 1, 1. Okay, D, I have a big Jacobian matrix is 2, 2, 2, 1, 0, -1, -1. And the rank is 2, and I'm happy. Let's consider E. The Jacobian matrix is 1, 0, -1, -2. And I see once again that the rows or the columns of this Jacobian matrix are independent in the terms of linear algebra. And once again, the rank is maximal possible rank. F, Jacobian matrix is -1, -1, -1, -2. The rank is 2. And the last case, G, I see that there are no such point. Yeah, I see that if x is 0, x plus y is 4, and x plus 2y is 6. I see that there are no solutions, because if x is y, if x is 0, then y is 4 and y is 3. That's not possible. So I'm happy. Finally, after considering all these cases, I can say that INDCQ holds. Yeah, but it's not so trivial like in the case of equality constraints. I need to check all possible combinations of equality constraints, because I now work with the situation of inequality constraints, and I'm not sure which one will be active before solving the problem. Okay, first step is done. Any questions about non-degenerate constraints, qualifications, conditions?
Yeah, I have a question for this. So there is only one method we were trying to do, right?
Only one?
There is only one way we are going to approach this optimization.
No, there are many ways. You may just abandon completely Lagrangian approach if you have no. So it depends on the text of the problem. If you have just optimized these functions and nothing said about the method, then you can say, "Oh, I hate Lagrangian approach. I will just do visual graphical analysis." That's okay. But my point is to illustrate Lagrangian function with inequality constraints. So I will, I'd like to illustrate with this particular problem the idea of INDCQ, of Lagrangian function, of first order conditions with inequality constraints. But if you have no requirements in the text, then this particular problem can be solved just graphically. So no, this is not the only way to solve this problem. But if we like to use Lagrangian multiplier, then we have 3 steps: INDCQ, first order conditions, and sufficiency check to classify points. but that's not the only approach. If it's not specified in the text, then okay.
Okay, thank you.
But are we going to have to consider these 6 cases, A, B, C, D, E, F?
Yeah, maybe some constraints are, yes, we need. It's like what we have done 2 months ago, because what we have done 2 months ago when we have considered MDCQ for equality constraints, we have considered only one case because all constraints were equal to some numbers. Yeah, we have equality constraints 2 months ago, and now we cannot be sure which one is active. Okay, so we consider all possible combinations. In general, you are right that if we work with linear constraints, then if they are not copying, if they are independent, then maybe we can start with even the 3 lines and see that. So sometimes it's easier to start with these 2, and if this matrix has rank 2, then each line apart has a rank 1. But to be honest, I have considered all possible combinations. Okay.
Thank you.
Okay, let's move on. Now, once again, that's not the only way to solve this problem. We can use visual graphical approach. That's okay if it's not specified. I look at the text of the exam and it's written, use Lagrange multipliers method to solve optimization problem. So without this explicit requirement, so sometimes Lagrange multipliers method is useful. Sometimes it's an overkill because you may analyze the problem graphically. In this case, it's required to do Lagrange multipliers method, but we can use graphical methods just, for example, to check sufficiency conditions. But we need Lagrange multipliers method. Okay. So we have standard way, and I will discuss a more parsimonious way to introduce Lagrange multiplier method in a case when we have non-negativity constraints. Okay, standard approach. I'd like to maximize x plus logarithm of y. I state all equations, all inequalities like bigger than 0. 4 minus x minus y is bigger than 0. 6 minus x minus 2y is bigger than 0. So I introduce Lagrangian function x plus ln y plus first lambda times x plus second lambda times 4 minus x minus y plus third lambda times 6 minus x minus 2y. Okay? Any questions?
No, it's clear.
Okay, let's just write a big system of first order conditions. Let's write a big system of first order conditions. dl dx is 0, dl dy is 0, lambda 1 is greater than 0, lambda 2 is greater than 0, lambda 3 is greater than 0, x original inequalities, x is greater than 0, 4 minus x minus y is greater than 0, 6 minus x minus 2y is greater than 0. Then they product dl d lambda I times lambda I is equal to 0. So I have 3 more conditions, like lambda 1 times x is 0. So basically that's, I just say that every added term is 0. lambda 2 times 4 minus x minus y is 0. Lambda 3 is 6 minus x minus 2y is 0. And basically that's all. It's a big system. How do I solve this system? My idea, so you are free to solve as you like. You are free to solve as you wish. You are free to start from every possible starting point. My advice first is to classify all cases. Consider cases. So that's my advice, but that's not a necessary requirement. So that's just an advice. I will have lambda 1, lambda 2, lambda 3, and I have 8 cases. Case A, case B, C, D, E, F, H. All lambdas may be positive, or one lambda may be 0. 2 lambdas may be 0. And all lambdas may be 0. My advice is to consider quickly all the cases. At first seems, wow, 8 cases. That will take enormous amount of time, but believe me, when you do something systematically, then you will save time on searching for errors, for considering the case you have missed, and so on. So my advice is just to be systematic. And I understand the difficulty that my screen is too small and I need to go up and down to consider every case. But in any way, let's indeed solve some cases. Yeah, let's solve some cases. How can I solve it? Because it's really fast. First, I will calculate dl with respect to dx. Dl with respect to dx is 1 plus lambda 1 minus lambda 2 minus lambda 3. dl with respect to dy is 1 over y minus lambda 2 minus 2 lambda 3. And basically now let's consider all the cases. Case A, if all lambdas are positive, lambda 1 is positive, lambda 2 is positive, lambda 3 is positive, I look on these equations where the product of lambda times inequality is 0, and I deduce that x is 0, 4 minus x minus y is 0, 6 minus x minus 2y is 0, and I see clearly that there are no solutions because if x is 0, then I cannot have 3 conditions as equalities simultaneously. Any questions? We have already solved case A.
Thank you. No question.
Okay, be brave. So if you don't care about someone else, just if you have no questions, just say me, yeah, I have no questions. No, it will be more interactive because sometimes if you just say it's too easy, it's okay, or it's too hard, I'm lost. That gives me information because otherwise I don't see. Okay, case B quickly. Lambda 1 is greater than 0. I hope I will not consider all the cases. I will just to show you the general idea that it's fast to consider simple cases. That is my point. So x is 0, 4 minus x minus y is 0. and I immediately see that x is 0, y is 4, and I need to check whether I can find lambdas. Just let's look at this equation. If lambda 3 is 0, I get 1 plus lambda 1 minus lambda 2 is 0. 1 over y minus lambda 2 is 0. And I see that lambda 2 is 1 over 4. And I have something like 3 over 4 plus lambda 1 is 0. Lambda 1 is minus 3 over 4. And that's forbidden. Negative lambdas are forbidden in optimization with inequality constraints. So once again, case B, no solutions. That's fast. Every case we consider step by step, and there will be, I don't remember in which one, it's a very old problem. It's in 8.
Can I ask you a question?
Yes, it's 8.
So in the case A, under lambda 3, we had 6 minus x minus 2y.
Yeah.
And in this case A, so you see under lambda 3.
Yeah, I see.
Yeah. And in case B, we didn't like include it. Why? You see, like you wrote 4 minus x minus.
Lambda, what is the case B? Case B is lambda 3 is 0. And if lambda 3 is 0, I don't know. Maybe.
Okay, I see now. All right.
Minus.
Thank you.
So that's the difference between two cases.
Yeah, I see it now. Okay, thank you very much.
When you have a 0 product, either the first term is 0, either the second one, either both terms are 0. Okay, let's go quickly. Case C, and you have lambda 1 is positive, lambda 2 is 0, lambda 3 is positive. So my conditions are x is 0, 6 minus x minus 2y is 0. I immediately get y is 3. Now lambda 2 is 0, so I have 1 plus lambda 1 minus lambda 3 is 0, and 1 over y minus 2 lambda 3 is 0. And finally, I get that lambda 3 is 1 over 6. And I think once again, lambda 1 is minus 5 over 6, but is not the case. Okay?
It's
clear.
So
Yeah.
which is 0, 0, 0.
No solutions here, no solutions here. Let's quickly exclude some more cases. Let us look at the third, at this equation, 1 over lambda minus lambda 2 minus 2 lambda 3. And I see that both lambda 2 and lambda 3 cannot be negative, cannot be 0. So I will exclude that is not the case, because if lambda 2 and lambda 3 are 0, and obviously there are no solutions, I will exclude that case. And that's already something. I have only 3 cases left, so let's consider them. And we will find a solution in one of these cases, or maybe there are no optimal point, but I hope, because that's a problem from the exam, so we should have at least one. It would be too easy for exam that there are no optimal point. Okay, let's move on. Oops, what should I copy? I will copy because my sheet of paper is like.
I'm sorry, can you scroll down a bit?
Yeah.
Point C. Yeah, thank you very much.
Just a moment, I will copy on the next, so I give you time to copy, or if you are solving simultaneously with me, because at my point of view, lectures are a little bit outdated. It's better that you solve with me. If you have problems, I help you. If you have no problems, then you're great. I will just copy my two equations, 1 plus lambda 1 minus lambda 2 minus lambda 3 is 0, and 1 over y minus lambda 2 minus 2 lambda 3 is 0. And I need to solve cases D, E, and F, 0 plus plus, 0, 0 plus, 0 plus 0. Let's move on to these three remaining cases. Case D, I have lambda 1 that is 0, lambda 2 that is positive, lambda 3 that is positive. I conclude that immediately that x plus y is 4, x plus 2y is 6. Then I see that y is 2 and x is 2. I have this point. And I think I need to check these constraints, like 1 plus lambda 1 minus lambda 2 minus lambda 3 is 0. And 1 over y minus lambda 2 minus 2 lambda 3 is 0. What do I have? I have that lambda 2 plus lambda 3 is 1. And lambda 2 plus 2 lambda 3 is 1 over 2. Yeah? And I see once again that lambda 3 is minus 1 over 2. No solutions for the case D. Okay, let's go to the, let's finish this problem. Let's consider, so my point that when you have a lot of simple cases, it seems at first, oh, I'm overwhelmed with a number of cases. It's 1, 2, and too many cases. But believe me, 8 easy cases will go much faster than 2 very hard cases. So I will go with E. Lambda 1 is 0, lambda 2 is 0, lambda 3 is positive. Okay, my system is 1 minus lambda 3 is 0, 1 over y minus 2 lambda 3 is 0. I immediately get that lambda 3 is 1. 1 over y is 2, so y is 0.5. And as lambda is equal, and as lambda 3 is greater than 0, then x plus 2y is 6. And finally, x is 5. Let me check that x plus y is less than 4. So we have no solutions here, if I'm not mistaken. Yeah, x plus 2y is 6. 1 minus lambda 3 is 0. 1 over y minus 2 lambda 3. I think it's okay. And finally, I hope we will find solution in the case F. Case F says that lambda 1 is 0, lambda 2 is positive, lambda 3 is 0. As lambda 2 is positive, then we have x plus y is 4. Anyone is with me? Everything is fine? You are lost?
No, I'm always here.
Yeah, we're good.
Yeah, it's good. Can you scroll a bit to the D, please? I didn't mention to copy. Yeah, thank you. Yeah, that's enough. Thank you.
Okay. Now I use the same equation. My original was 1 plus lambda 1 minus lambda 2 minus lambda 3 is 0. 1 over y minus lambda 2 minus 2 lambda 3 is 0. So I plug in the case I'm considering, and I have 1 minus lambda 2 is 0. 1 over y minus lambda 2 is 0. I get lambda 2 is 1. And y is 1. And x is 3. So basically, we need to check all the constraints. So we have x is greater than 0, that's satisfied. X plus 2y is less than 6 for 3 and 1, it will be 5, it's satisfied. And everything else is fine. Yeah. We need, no, everything
X
else
plus
is,
y as well.
sorry?
X plus y, the constraint.
Y is 4.
Yeah.
So the condition is certainly satisfied. It's satisfied as equality. So, okay. Woohoo! Wow. One suspicious point. It was not done specially. I have just considered a problem from a retake exam, and I was so unlucky that I found the solution in the last considered case. It was not planned before this lecture. It just coincidence that the last case I have considered has a solution that it's it just I had a bad luck today. Okay, so we have finally solved first order condition. Lambda 1 is 0, lambda 2 is 1, lambda 3 is 0, x is 3, y is 1. This is unique point A. Okay, first order condition is satisfied.
Excuse me, what about points G and H?
We have considered them very fast. Yes, because if you look at the equation star, we have equation star, dl with respect to dy is 0. And we see that if both lambdas are 0, lambda 2 and lambda 3, then it happens that 1 over y is 0. That is impossible.
Okay.
And in both cases, so I have considered them, and so I see that lambda 2 is 0, lambda 3 is 0, lambda 2 is 0, lambda 3 is 0, and looking at the equation star, dl with respect to dy is 0, I conclude that these two lambdas, lambda 2 and lambda 3, cannot be 0 simultaneously. They can be 0, but not simultaneously. Okay?
Yes, thank you.
Okay, we have solved first order conditions. So, but that's you perfectly know. Two new points I would like to discuss is to work with second order conditions and to simplify first order conditions when you have a special type non-negativity constraint. So this is all the topic. Basically, we have discussed how to solve this problem. So this is just a little bit of practice, but for the moment, nothing new was explained. So now we go back to, well, no, not to go
Sorry,
back. We go.
may I ask a question?
Yes.
I already typed the question in our chat.
Sorry. In the chat. How to solve H? In the point, in the case H, you have lambda 2 is 0, lambda 3 is 0, and it's impossible to have lambda 2 and lambda 3 0. So there are no solutions for the case H. Okay? Case H contradicts the condition that the derivative of L with respect to y is 0.
Зависло, да?
Да, он завис.
Я думал, он на тофлами.
Let's wait for a while.
Oops. The connection, I think, was lost. Just a moment.
Yeah.
Well, just a moment. Yeah, the connection was lost, but I see from my computer that my tablet is working now. Yeah.
Yeah.
Yeah, we see you.
SOS.
Okay. Sometimes it happens. I don't know why, but just a small glitch in the connection. Okay, we are ready to go on. The recording is working. Yeah, everything is fine. Else, that was a small glitch in connection. Okay, how can we check? So my hierarchy of ideas is the following. Check graphically if you can. Check graphically if you can. Second approach, use Weierstrass. It's written Weierstrass theorem. Use concavity. And the last one is to use bordered Hessian matrix of active constraints. So I prefer to graph. If the graph is too hard, for example, I have 3 or 4 variables, then try to use Weierstrass theorem. If Weierstrass theorem is not applicable, then try concavity convexity of a function. If it's not applicable, then go with H, and the 5 is just maybe, or maybe even before here, maybe 0, just think a little bit, ponder the, because sometimes you just think, oh yeah, see that the maximum exists. Okay, let's graph. We will not think, we will just graph, and we will discuss that approach, because basically Weierstrass theorem and concavity, they work like in the case of equality constraint, but we will discuss, I think, concavity next time in more details. Okay, let me graph. My constraints are x is greater than 0, x plus y is less than 4, x plus 2y is less than 6.
Он опять завис, да?
Да.
Да, похоже.
О, да.
Опять пропала связь.
I think it's stuck for a while. Let's wait. Hello. Hello, welcome back. Oh, what happened?
Okay, we are back
Okay.
once again. I'm sorry, but I can't do nothing.
It doesn't matter. We will have some time to read the script. It's okay.
Okay, let's continue. And we need to draw also x is greater than 0. So we need to use that part. Y is strictly greater than 0 because I have logarithm of y. And finally, I need to draw the line x plus 2y is 6. It will go like, I will have 3 there, and I will have 6, and oops, and I need to use that part of my plot. And finally, I have this figure with 4 sides. Yeah, I have 4 sides. I have an intersection at point A. Point A is a solution of this system, and I see that y is 2, x is 2. So that is my constraint set, where I'm searching the best point. My goal function is to maximize x plus logarithm of y. I need to maximize. I draw a level curve of this, sorry, C. I draw the level curve for this function. X is C minus logarithm of y. C minus logarithm of y works like what is it? It will be.
Sorry, but I suppose that point A was x equal to 3 and y equal to 1.
Yeah. Maybe it's not a point A. Let it be point intersection. That's intersection point. I don't. Yeah, you're right. It's not an optimal point, but it's a point that is important on our plot. Yeah.
Okay, thank you.
Yeah, I agree that it's not a point A. Yeah, you are right that the suspicious point is x is 3, y is 1, and lambda 1 is 0. I have copied all the details. Okay, this is suspicious point. So my suspicious point is there, 3, 1. Okay, and we need to draw level curves of this function. We know that logarithm is increasing function, minus log is decreasing function, and the C minus logarithm of y, we will just move level curves to the left, to the right, and basically level curves will be like this. Because we have a suspicious point, so we have a tangent line at this point. This is one curve, and we just move this curve to the right or to the left. And
will suspicious points always be a tangent to the constraint? I mean, like,
yes, necessary conditions. We have discussed the intuitive idea of necessary conditions.
just like,
yes, they will be, because what is the problem? They will be tangent. Yeah, that's the role of necessary conditions. Yeah, but yeah, probably you have one exception when it is not possible to have a tangent. Yeah.
boundary point.
You may have a condition like so not in this problem, but in some alternative problem, alternative setup, in some other problem, not in this one, you can have something like, if you consider another function, you may get best point here. And it's not tangent at all, but it cannot be like, so basically a suspicious point is suspicious not for nothing. So if it's possible to have a tangent there will be a tangent. In this case, it's like kink, and you have no possibility to have a tangent on the kink. Or you have even the possibility to have like that one, but In this case, yes, it's a tangent because we have lambda is positive and negative depending on whether the condition is active or not.
Okay, thank you.
Excuse me, and can you explain one more time why lambda the second is equal to 1?
Okay, but I will do it a little bit fast. If I consider the question, the case F, I have two standard equations. This is dl dx is 0. The second is dl dy is 0. If I look carefully at the first equation, I plug in the assumptions of the case. My case F starts with lambda 1 is 0.
Oh,
lambda
yeah.
6.
Now I see. Thank you.
Okay, now let me draw the gradient of the function. Let me draw the gradient of the red function, of the goal function. And x should be bigger and y should be bigger. So my gradient is somewhere is pointed to positive direction in x and y axis. So the gradient goes there. And I clearly see that my suspicious point is maximum, because I would like to increase x, to increase y, but to increase x and increase y, starting from the point A, I should violate my constraints. I'd like to go higher and to the right, but it's not possible given my constraints. So this point is a local constraint extrema maximum point. Okay?
Okay, thank you.
Because to be better than in a point A, I should go into the red region to have better values than in the point A. I should move from the point A to better region, and this better region is inaccessible to me if I am at the point A and I don't like to violate my constraint. Okay? That is the graphical way. That's my preferred way. Why it's my preferred way? Because you may, for example, spot some errors. So, for example, imagine that you solve a real problem on the exam and you make some errors in the first of the condition. That may happen. And on the plot, you may spot them. If, for example, you see that it's not possible to have a, so from the plot, it's not visible that my point is exactly 3, 1. But if I would get that extrema is, I don't know, at the point 5, 1, I would say, oops, 5, 1 is certainly not possible. And sometimes it's, the idea you can spot previous errors on the graph. And that's why it's my preferable way. So that's a good check that the extrema is more or less logic.
Boris, I'm sorry.
Yeah.
Can you repeat how can we spot it from the graph? The missed points.
But if you see that the maximum, basically, when we solve first order conditions, we do not use the plot, the graph. And if in this case, it's more or less obvious to have an extrema somewhere on this line. Yeah. So if I would have an extrema here, so for example, you have an extrema there on the plot, you see immediately, yeah, you can move in the upper right direction. It's not an extrema. Yeah. So not all. I agree with you that not all errors can be spotted on the plot. but some errors can be spotted because it's like independent way to intuitively approximately find an experiment. Okay?
Excuse me. So by this theory, x and y can both become better, right?
Yeah, to make our function bigger, we need to go into the red part from the point A, and then the goal function will be bigger, and that is not possible to go from the point A in the red region.
Yeah, thank you.
Okay, let's move on to second order condition by Weierstrass theorem. So I will explain. So we have already solved the second order condition, but I'd like to point out that if you cannot plot, use Weierstrass theorem. In my case, x plus y is greater than 4, x is greater than 0, y is greater than 0 because of logarithm, yeah, and x plus 2y is less than 6. In this case, Weierstrass theorem cannot be applied. Why it cannot be applied? What is the problem?
Because our set is not closed.
Yeah, it's bounded but not closed. Yeah, we may draw a big circle to bound it. Yeah, it's very our set does not extend to infinity. It's bounded. Our set is bounded but not closed. Why it's not closed?
Because y is strictly greater than 0.
Yeah. So this line is excluded from optimization. Y is strictly greater than 0. So Weierstrass theorem is not applicable here, but my advice is just try to do the plot. If you have 3 variables, okay, plot is impossible for 3 or 4 variables, but sometimes you can draw even in 3 dimensions by using sections. Okay, Weierstrass theorem is not applicable here.
Can I ask you one question real fast? So like the point we found was y equals 2 and x equals 2. Is that correct?
No. To draw a plot, we have found the intersection point. Point I is just intersection of these 2 lines. But the only suspicious point we have found using first order conditions, that is the only suspicious
Oh, yeah,
point.
yeah, 3 and 1. Okay, yeah. Okay, все, теперь я понял, да, я запутался немножко, все.
So,
sorry.
I is not a suspicious point. It's just a like 3 here. It's just a important point on a plot, but it's not suspicious. Okay, it's a point of a kink.
Yeah.
Okay, let's move on.
And one thing, why did we write a equals well, like a the system x equals 3, y that's the point. Все, теперь я понял. Все, вопросов нет. Все.
Can you explain one more time why Weierstrass theorem is not applicable here?
Why what?
Why we can't use Weierstrass theorem? Like I understand that's bounded, but why it's not like what's the problem with y?
It's not closed. What is a closed set? Closed set contains its boundary. Yeah.
Yeah.
But if you consider a point like the problem is this with points. If you consider a point, like x is 1, y is 0, this point is not in our, let's call it our, so it will be D, our, this point is not in D, but this point is on the border of D, yeah? It's a limit points for D. You can approach this point by a sequence of points in D. Okay.
Yes. Okay. Thank you. Yeah, because I didn't see the condition about y from the natural logarithm function. Now I see it.
Yeah. Yeah. It should be strictly greater. Okay. So concavity we will discuss next time. And for today, now we have the fourth idea. We can use second order condition for active constraints. So just as we have used second order conditions 2 months ago, we just use the same logic, but we use active constraints. What is active? Active means equality constraint. If I consider the point A, x is 3, y is 1, I have x greater than 0, x plus y less than 4, x plus 2y less than 6. So this one is strictly greater than 0, that one is equal to 4, and the third one is strictly less than 6. So I have one active constraint. That one is active at the point A. And so when I will create bordered Hessian matrix, I will consider only this only this constraint number 2. Okay.
Okay.
Okay. Let's consider Hessian matrix. So I will have 0 here. So I will take derivatives only of the active constraint. So it will be 1, 1, 1, 1 with respect to x, y. Yeah. This is with respect to lambda, with respect to x to y, x, y. Oh, I need dl with respect to dx squared, dl with respect to dy squared, and I need to dl with respect to dx dy. Oh, my Lagrangian function was, I don't remember, x plus, sorry, a logarithm of y plus lambda x plus lambda 2, 4 minus x minus y plus lambda 3 x 6 minus x minus 2y. Yeah. So we have no x squared, so this is 0. With respect to x, y, we have no product x times y, so it's 0. That one we have because we have logarithm, and the derivative will be, I think, minus 1 over y squared. Yeah.
Yes.
Minus 1 over y squared. So my bordered Hessian matrix. So the only particularity here is just when you are constructing bordered Hessian matrix, you do not consider all the constraints. You consider only active constraints. You do not consider all the constraints. Only active constraints are included in Hessian matrix when we work with inequality constraint. That's the only difference we have. So H at the point A is 0, 1, 1, 1, 1, 0, 0, 0, and it will be minus 1, I think. And as you remember, we have one active constraint. So we have two variables. we have one active constraint. So we need to check how many determinants we will check. So we work like 2 months ago, we work with one constraint, not with 3 constraints, but with one constraint. What was the condition for maximum when you have one constraint? Only active constraints do count. What is the
Check n minus k constraint last order principal minor. So we should check the last one.
yeah,
mean.
we check the last one principal minor, yeah, delta 3, and for maximum, delta 3 should be positive, negative.
-1 to the power of the constraint.
Minus power 1 to the power
It should be negative.
n to the power n.
I think it should be positive.
To be positive definite, it should be less than 0.
We have it to be the negative difference.
It should be positive for maximum. Because I have one constraint, so I flip the sign. So it's very easy to memorize. So imagine a situation without constraint. Sorry, it's delta. No, it's okay. It's delta 3. Yeah. Sorry, sorry. Just a moment. Maybe I'm confused. Just a moment. For maximum, normally, I have for minima I have plus, 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 plus. For maxima, I have minus, plus, minus, plus, and so on. I flip the sign. No, I'm correct. No, this is without constraints. So I remember conditions without constraints. So I have one constraint. I flip all the sign, and one constraint I have for maximum plus, minus, and so on. For minima, I have minus, 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 and I check only one minor. I look at the first line, so it should be plus. Okay, so let's check delta 3. Delta 3 is, let me add 3 lines below, 0, 0. So delta 3 is 0 times 0, 0. 1, 0, 0, plus 0. Tin, 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 plus 0. Then I subtract 1 minus 0, minus 0, minus 1, it's 1. So delta 3 is 1. And bingo, point A is a local constraint extrema. Okay, any questions?
Okay, thank you.
So we see one more advantage of graphical approach. When we solve the problem graphically, then we simultaneously can be sure that the maximum is global. Yeah. So when you work with Hesse matrix is a local idea. But when we work with plot, we see that even if I move to the other side of my black figure, red function will be lower even on the opposite side of my figure. So I see from this analysis, graphical is better. I see that point A is a local and global constraint extremum. Okay, graphical analysis is better, so I prefer to work with plots. But anyway, if plotting is not available, or for example, if you are asked explicitly on the exam, that happens sometimes, rarely, but it happens, that use bordered Hessian to check second order conditions. Then I use only active constraints in my bordered Hessian. Here I use only active constraint, only constraint number 2. But in general, my advice, if you are not required, go with plots. Okay, and finally, one more new idea. Non-negativity constraints. Non-negativity constraints.
Shouldn't we check at the previous page like other variants of like we checked like the two constraints were non-active, one active? Shouldn't we check that the other is active while the other two are inactive?
No. We have one suspicious point. The problem is that we have a guarantee that all suspicious points were we have catched all suspicious points by solving first order conditions. And we have considered 8 cases, A, B, C, D, and so on. And we have only one point. Y is equal to 3, X is equal, X is equal to 3, Y is equal to 1, yeah? We have only one suspicious point. At this suspicious point, only one constraint is active. So here we do not consider other cases.
Okay, yeah, okay, thank you.
So if I have another point B, imagine that I have another point B, and for example, if in the first order conditions, if in other life, yeah, if in other life point I was suspicious point, it's not the case in our problem, but if it was, then I will check a big bordered Hessian for the point I, okay?
Yes, okay, thank you. So like we derived the signs of the constraints from the from the moment where we considered all 8 cases and we picked the right one, and we have the same signs in the constraints.
Yeah. So basically, for example, if I would catch that point as a suspicious point X, yeah, some point R, this point, I have no active constraints in R, and so I will remove the border from my Hessian matrix. So I just have a collection of suspicious points, and I check separately every suspicious point. In one suspicious point, my Hessian matrix can be with border. In other suspicious point, in other critical point, my Hessian matrix will have 2 active constraint, another 1 active constraint, and was a 0 active constraint, okay? And I check and I construct a particular Hessian bordered matrix for each critical point.
Yes, okay, thank you.
Okay, and finally, one more new topic, non-negativity constraints. Because we have considered 8 cases, 8 is too much. I think many of you were lazy, and not all of you have considered all 8 cases with me. So I'm also lazy. That's normal to be lazy, at least sometimes. And when I have so basic intuitive idea is very simple. If I have a function of one variable and I have a non-negativity constraint, when I maximize this function, it may happen that the derivative in here is 0. Yeah, that's possible situation for extremum. it may happen that here x0 is extremum. It may happen something like that. X f of x. Once again, x equal to 0 is extremum. Why? Because I have non-negative constraint. And in the other case, when I have something like this, in this case, x equal to 0 is not an extremum. So basically, if you combine all these three cases into some equations, you may say that x is greater than 0, f prime with respect to x is less or equal than 0, and x times f prime of x is 0. So if you combine all these three graphs into the system of equations and inequalities, you will have the system like this. And basically, you can do the same thing with inequality constraint, with a general case. So let's move on to general case. This is the idea. Now the general case. So if you have a constraint like that, or maybe some more constraints, I don't care. I will focus on that one. And you normally should do something like this. F prime of x, y, z plus lambda times x plus lambda 2 times some other constraint plus lambda 3 some other constraint. I have a very special type of line here, and look carefully. dl with respect to dx is df with respect to dx plus lambda plus d, let it be g2, g3, g2, g3, dg2 with respect to dx lambda 2 plus dg3 with respect to x just lambda 3. That should be equal to 0. Lambda 1 should be non-negative, and lambda 1 times dl times dl d lambda 1 should be 0, or lambda 1 times x should be 0. So I have three conditions related with my unique inequality. And that's awful. And the idea, we can introduce parsimonious Lagrangian function. We will just remove, we will not introduce lambda 1. We don't need lambda 1. We will say that it's f prime. This is parsimonious version. We do not copy that one. Plus lambda 2 times g2 plus lambda 3 times g3. And let's see the derivative of parsimonious Lagrangian function. It will be df dx plus dg2 dx times lambda 2 plus dg3 dx times lambda 3. And we see that this lambda is non-negative. So the derivative of parsimonious lambda should be non-positive. Okay? Yeah? Because if I add something that is positive or 0, I get 0. So the remaining part is non-positive. Okay? Anyone?
Yes, it's clear.
Okay, so lambda is just, if you see, lambda is just minus dl parsimonious with respect to dx, and this equation may be stated like, and x is greater than 0, dl prime with respect to dx times x is 0, and x is greater than 0. So that's a parsimonious version of the same conditions. So it's great to have this case because I have, so let's count how many conditions do I have in my original version. I have 1, 2, 3, 4 conditions. And in my simplified version, I have 1, 2, 3 conditions, and 1 variable less. So in original Lagrangian function, I have 4 conditions and lambda 1. In my simplified parsimonious version of Lagrange Lagrangian function, I have 3 conditions and 0 instead of lambda. So I have no lambda 1 at all. I have 1 parameter less. That's great. Other conditions are just the same. So because G2 is some big complex function, so basically the idea is the following. If you have a inequality like x is greater than 0, instead of introducing special lambda for it, you may just do not introduce lambda and write in first order conditions x is greater than 0, dl with respect to dx is less than 0. That will be parsimonious version of Lagrangian function, and x times dl with respect to dx is 0. So you have another way to write first order conditions. You just forget about this term. You do not include it into the Lagrangian function, and you just change a little bit first order conditions. You have less or equal than 0, and we have 0 here. Okay?
Excuse me, and can you explain once again why would we have less or equal than to 0?
Look at my original non-parsimonious version of Lagrange of this condition. dl with respect to dx, L is original with lambda 1 plus x introduced there. Okay? You see that lambda 1 is just, if you move everything else to the right-hand side, yeah? If you move everything else to the right-hand side, you will see that lambda 1 is just minus the derivative of parsimonious Lagrangian function.
Mm-hmm.
Okay?
Yeah, okay.
But lambda is positive. So parsimonious Lagrangian derivative is negative.
Oh, yeah. Now I see. Thank you.
Why is it negative? Sorry.
Because lambda 1, okay, so let's express lambda 1. Lambda 1 is minus df with respect to dx plus dg2 with respect to dx plus lambda 2 plus dg3 with respect to dx plus lambda 3 is minus the derivative of parsimonious Lagrangian function with respect to x, okay?
Oh, yeah. Now it's clear. Thank you very much.
And lambda is non-negative, so it means that the derivative of simplified parsimonious Lagrangian function is negative. or 0. Or you may get this idea intuitively in a very simple case when there are no other restrictions. Basically, this is the case when there are no G2 and G3. And from plots, you see that when there are no G2 and G3 restrictions, then basically from plots it follows that x should be greater than 0, f prime may be 0, f prime may be negative, but it cannot be positive. And x times f prime should be 0 because it's not possible to have an extrema there. Yeah, negative sign of derivative is possible, but at 0. And basically, if you add the constraints G2, G3, this will be generalized to this part of the first order conditions. Okay?
Yeah, thank you very much.
And the honest proof is here. So if we add G2 and G3, they do not influence our work with first x. So basically, what we have covered today. Today we have considered one more example of optimization problem with. So let's have a small resume. Okay, so I advise you to consider cases. Consider small cases when you solve for first order conditions solution. Second point, when you check second order conditions, when you classify points using graph, and if it's not possible to classify points using graph, okay, then use Weierstrass, then use concavity. We have not discussed concavity today. If it's not possible, then go with bordered Hessian matrix. Bordered Hessian matrix. The important point here that we use only active constraints. And the last point, instead of full, when you have inequality constraint that some variable is non-negative, it happens very often. So you may have a full Lagrangian function, and for full Lagrangian function, you have a dl with respect to dx is 0, lambda is greater than 0, x is greater than 0, d lambda times x is 0. You have 4 constraints, and you can use parsimonious Lagrangian function. In parsimonious Lagrangian function, you do not include at all this term. You just, let's forget about this term. Yeah, we are lazy. In that case, you change a little bit your first order condition. The first derivative is non-negative. You have no lambda. X is and the derivative of simplified Lagrangian function times x is 0. So you have, that is why it's better. It's better because you have 3 conditions instead of 4, and you have 1 variable less. That's great. 3 conditions instead of 4, just for free. Just for free. You have one condition less, 1 variable less. That's great. And in this case, you will consider 4 cases while solving first order conditions. Okay, basically we have used a lot of time. Just that's all. If you have any questions, just write me and we will discuss them. Have a nice evening.
Nice
evening.
evening.
Yeah.
Можно на русском задать, да? Или...
Yeah, I understand Russian.
Когда мы смотрим Bold Inhesion Matrix и определяем, какие у нас constraints active, а какие non-active, это же мы понимаем в зависимости от точек, которые мы получили, когда система изначально.
Exactly, you're completely right. In one point, you have one active constraint. In the other point, where you have two active constraints. Yeah, you are completely right. We should obtain points before checking second order conditions. You cannot do it. Oh, this is general formula. No, you have the size of my Hesse matrix will be different in one point, in the other point. Yeah, you are completely right.
Хорошо, спасибо большое.
Okay, so bye-bye. See you next time.
Bye. See you. Have a good weekend.
Thank you. Goodbye.
Thank you very much, Boris Borisovich. Have a nice evening. Goodbye.